In 2024, a Chinese power company strung a transmission line across a river valley in Jiangsu province using a cable that contains almost no copper at all. The line carries more current than the copper line it replaced. It weighs less than half as much. It cost a fraction of the price. And when the engineering data was published, electricians and cable specialists around the world read the numbers and said the same thing. That should not work. Copper has been the undisputed king of electricity for more than 140 years. Every serious engineer learns the same lesson early on. If you want to move electricity efficiently, you use copper. Everything else is a compromise. Aluminum is cheaper, but weaker. Steel is stronger, but conducts badly. Silver is better, but absurdly expensive. Copper sits in the perfect middle, and that is why it ended up inside the walls of nearly every building on Earth. But China has a problem with copper, a very expensive, very strategic problem. And over the last decade, engineers there have been quietly building an alternative that does not just imitate copper. In some situations, it beats it. If you are enjoying videos like this, please hit the like button, because these take a lot of research to put together, and subscribe so you do not miss the next one. What you are about to hear involves metallurgy laboratories, carbon fiber, giant spinning machines, and a material that behaves in ways that traditional electrical training says it should not. But to understand why this cable matters, you first need to understand why copper became so important in the first place, and why China desperately needed a way out. Think about the wires behind the wall of the room you are sitting in right now. Somewhere in that wall, there are thin strands of orange metal carrying electricity to your lights, your outlets, and your appliances. That metal is copper. Go outside and look at the power lines running down the street. Follow them back to the substation, then to the transmission towers, then all the way back to the power plant. Copper is everywhere in that chain. It is in the generators. It is in the transformers. It is in the motors. It is in the chargers. Copper became the standard for two reasons. First, it conducts electricity extremely well. Only silver is better, and silver is far too expensive to string across a countryside. Second, copper is ductile. That means you can pull it into thin wires without it snapping. You can bend it around corners. You can twist it into a screw terminal, and it will hold. It is forgiving. Electricians love it because it does what you expect it to do. For most of the 20th century, this was not a problem. Copper was abundant enough. It was mined in Chile, in Peru, in Zambia, in the United States, and in dozens of other places. There was always more of it available if you were willing to pay. Then the world changed. Every part of the modern economy started demanding more electricity at exactly the same time. Electric vehicles need enormous amounts of copper. A single electric car can contain 4 times the copper of a gasoline car because of the motor windings, the battery cables, and the charging system. Wind turbines need copper. A single large offshore turbine can contain more than 30 tons of it. Solar farms need copper for their collection systems. Data centers need copper for their power distribution. And on top of all that, entire countries are electrifying their heating and their industry. The demand curve went almost vertical, but the supply curve did not. Here is the uncomfortable truth about copper mining. Copper does not come out of the ground in neat orange blocks. It comes out as rock that contains a tiny percentage of copper by weight. In the best mines a century ago, ore might have been several percent copper. Today, many major mines are working with ore that is well below 1%. That means you have to dig up, crush, and process an enormous amount of rock to get a single ton of usable metal. The mines get deeper, the energy required goes up, the water required goes up, the waste goes up, and the cost goes up with all of it. Opening a brand new large copper mine is not a quick project either. From the moment a company finds a deposit to the moment the first metal ships, the timeline is often 15 to 20 years. There is exploration, permitting, environmental review, financing, road building, and construction. The world needed more copper immediately. The mining industry could only offer it slowly. Now add the strategic layer. China is by far the largest consumer of copper in the world. It uses a huge share of everything the planet produces. But China does not have anywhere near enough copper in its own ground to feed that appetite. It imports the vast majority of what it uses, either as raw ore or as refined metal, from mines scattered across South America, Africa, and Central Asia. Think about what that means from a planning perspective. Your entire electrical grid, your entire vehicle industry, your entire renewable energy build-out. All of it depends on ships arriving from the other side of the planet carrying a metal you cannot make yourself. Prices are set by markets you do not control. Shipping routes pass through waters you do not control. Mining contracts sit in countries whose politics can change overnight. For a country planning decades ahead, that is not a supply chain. That is a vulnerability. So, the question was asked, and it was asked seriously and repeatedly. What if we simply stopped needing so much copper? The obvious candidate was aluminum. And the electrical industry has a long, complicated, and somewhat painful history with aluminum. Aluminum is not a bad conductor. It carries electricity reasonably well. It is far lighter than copper, roughly 1/3 of the weight for the same volume. And critically, China has aluminum, enormous amounts of it. Aluminum is refined from bauxite, and the refining process is essentially a way of turning huge amounts of electricity into metal. China has the smelting capacity and the power generation to make aluminum at scale. It is a domestic material, not an imported one. For long-distance overhead transmission lines, aluminum already won that argument decades ago. If you look up at a high-voltage tower almost anywhere in the world, the conductors hanging from it are aluminum, usually wrapped around a steel core for strength. Copper is simply too heavy to string across hundreds of kilometers of towers, so the industry accepted the compromise and moved on. But when it came to everything else, aluminum had a terrible reputation, and it earned it. In the 1960s and 70s, when copper prices spiked, builders in North America began using aluminum wiring inside houses. It seemed like an obvious cost saving. It turned into a decades-long disaster. There were several reasons why. The first is a phenomenon called creep. Aluminum is soft, and it flows slowly under sustained pressure. When you tighten a screw terminal onto an aluminum wire, the metal slowly squeezes out from under the screw over months and years. The connection loosens. A loose connection means resistance. Resistance means heat. Heat means fire. The second reason is thermal expansion. Aluminum expands and contracts more than copper as it heats and cools. Every time the circuit is loaded and unloaded, the wire grows and shrinks slightly inside its terminal. Over thousands of cycles, that motion works the connection loose all by itself. The third reason is oxidation. When aluminum meets air, it instantly forms a thin layer of aluminum oxide on its surface. That oxide layer is tough and protective, which is great for aluminum siding on a house, but it is also a poor conductor of electricity. So the very surface you are trying to make contact with is coated in something that resists current. Copper oxidizes too, but copper oxide still conducts. Aluminum oxide effectively does not. Put those three problems together and you get warm outlets, scorched switch plates, and house fires. Regulations tightened. Insurers raised rates. An entire generation of electricians learned to distrust aluminum on site, and they taught that distrust to the generation that followed. In many trades, aluminum in a building became something close to a swear word. That is the wall Chinese engineers ran into. It was not a physics wall. It was a materials and reputation wall. Aluminum was not fundamentally incapable of carrying electricity. It was just bad at everything that happened at the ends of the wire and over time. So the research question was reframed. Nobody set out to make pure aluminum acceptable. Instead, laboratories across China started asking a different question entirely. What if we stopped treating aluminum as a cheap substitute and started engineering an entirely new alloy designed specifically to fix each of those failure modes one at a time? That is where this story gets genuinely interesting. Metallurgy is a bit like cooking, except the ingredients are elements and the oven runs at temperatures that would vaporize a kitchen. When you make an alloy, you take a base metal and add small quantities of other elements. Sometimes we are talking about fractions of a percent. Those tiny additions change how the atoms arrange themselves as the metal cools, and that arrangement determines everything about how the finished material behaves. The alloys that came out of this work are broadly known as aluminum alloy conductors, and the recipes vary depending on the manufacturer and the application, but the general approach is consistent. Small amounts of elements like iron, magnesium, copper, boron, and various rare earth elements get introduced into the aluminum in carefully controlled quantities. Each addition has a job. Some of them are there to stop creep. By introducing elements that form tiny hard particles distributed throughout the metal, engineers effectively pin the internal structure in place. The aluminum atoms can no longer slide past each other so easily under pressure. The metal keeps most of aluminum's lightness while gaining a resistance to slow deformation that pure aluminum never had. When you tighten a screw on it, it stays tightened. Some of them are there to improve strength and flexibility at the same time, which sounds contradictory. Normally, when you make a metal stronger, you make it more brittle. It resists bending, and then it snaps. The trick these alloys use is a combination of composition and heat treatment. The metal is heated, held, and cooled on a precise schedule, which lets specific crystal structures form inside it. The result is a wire that can be bent, coiled, pulled through a conduit, and bent again without cracking, while still holding far more tension than ordinary aluminum. And critically, the alloy design tries to do all of this without wrecking conductivity. This is the hardest part of the whole exercise. Every element you add to a pure metal disrupts the neat lattice of atoms that electrons travel through. Disrupt the lattice, and you increase resistance. It is a constant balancing act. Add too much of your strengthening element, and you have created a beautifully strong wire that is terrible at its actual job. The alloys that came out of this process typically conduct somewhere in the low 60% range compared to copper, measured by the International Standard Scale. On paper, that sounds like a clear loss. Copper wins, case closed. Except that is not how cables actually get judged in the real world. Here is the piece that trips people up, and it is the reason so many experienced electricians look at these claims and instinctively reject them. Copper conducts better per unit of volume, but aluminum alloy conducts far better per unit of weight because it is so much lighter. Roughly speaking, a kilogram of this alloy will carry about twice the current of a kilogram of copper. That distinction changes everything, because cable is sold by weight, shipped by weight, hung by weight, and supported by weight. So the engineering answer is straightforward. You use a slightly thicker conductor. If the alloy carries less current for a given diameter, you increase the diameter. The finished cable ends up physically larger than the copper equivalent, but still dramatically lighter and dramatically cheaper. But increasing the diameter of an overhead conductor creates a new problem. Bigger cable means more weight per span and more wind resistance, which means more stress on the towers holding it up. And that is where the second half of this technology comes in, and where it stops being a simple material story and becomes a genuinely clever piece of engineering. Traditional overhead power lines are built around a core of steel. The aluminum strands do the electrical work, and the steel core carries the mechanical load, holding the cable up between towers that might be hundreds of meters apart. It is a sensible design, and it has worked for a century. But steel is heavy. Steel also expands significantly when it gets hot, which causes the line to sag on hot days or under heavy load. Sagging lines are a serious operational problem. They reduce clearance to the ground and to trees, and utilities have to limit how much current they push through a line specifically to keep it from sagging too far. Steel is also magnetic and electrically conductive in an unhelpful way, which produces losses inside the cable itself. So Chinese manufacturers began replacing that steel core with a composite core built from carbon fiber and glass fiber bound in resin. If you have ever held a carbon fiber bicycle frame or a tennis racket, you know how strange the material feels. It seems impossibly light for how rigid it is. Pound for pound, carbon fiber composite is stronger than steel. It does not corrode. It does not conduct electricity. And crucially, it barely expands at all when heated. Its thermal expansion is a small fraction of steel's. Swap the steel core for a composite one, and several things happen at once. The cable gets much lighter overall, which means you can hang more conductor between the same towers. The sagging problem largely disappears, which means the utility can run far more current through the line without violating clearance rules. In practice, replacing a conventional conductor with a composite core aluminum alloy conductor on the same towers can roughly double the carrying capacity of that line. Think about what that means for a country trying to move enormous amounts of renewable electricity from windy, sunny, western regions to the dense industrial cities on the eastern coast. You do not need to build new towers. You do not need new land rights. You do not need new corridors cut through farmland and mountains. You restring the existing towers with a better cable, and the line carries twice as much power. That is an extraordinary return on a relatively modest investment. Now, none of this happens in a laboratory beaker. Turning a promising alloy recipe into millions of kilometers of usable cable requires an industrial process on a scale that is hard to picture. It begins in the smelter, where aluminum is held as a glowing liquid in enormous furnaces. The alloying elements are introduced in precise quantities, and the mixture is stirred and held at temperature to make sure the distribution is even throughout. A batch with uneven composition produces cable with unpredictable properties, and unpredictable is the last thing you want inside a power grid. The molten alloy is then cast into a continuous rod. In modern plants, this is a continuous casting and rolling line, where the liquid metal is poured at one end and emerges at the other as a long, solid rod moving steadily along rollers. The cooling rate at this stage matters enormously. Cool it too fast and you lock in the wrong internal structure. Cool it too slow and the strengthening particles grow too large and stop doing their job. That rod then goes to the drawing machines. The rod is pulled through a series of hardened dies, each one with a slightly smaller hole than the last. Each pass squeezes the metal thinner and longer. The wire speeds up as it gets thinner, and in a modern plant, it comes off the final die moving fast enough that it is a blur. All that squeezing works the internal structure, which is why the heat treatment afterward is so important. The wire is annealed in controlled ovens to bring it back to exactly the combination of strength and conductivity the specification demands. Meanwhile, in a separate part of the operation, the composite core is being made. Thousands of individual carbon fibers, each one thinner than a human hair, are pulled through a resin bath and then through a heated die in a process called pultrusion. The resin cures as the bundle passes through, and what comes out the other side is a continuous solid rod that is astonishingly strong and light. A layer of glass fiber is usually applied around the carbon to prevent a chemical reaction between the carbon and the surrounding aluminum, which would otherwise cause corrosion where the two materials touch. Then everything comes together in the stranding machines. These are large rotating cages, sometimes several meters across, that spin while feeding dozens of individual wires inward toward a central point. The core runs through the middle. The alloy strands wrap around it in a helical pattern, layer after layer, each layer wound in the opposite direction to the one beneath it, so that the whole assembly holds itself together under tension. Watching a stranding machine run is genuinely hypnotic. It looks less like manufacturing and more like an enormous mechanical loom weaving metal rope. For insulated cable, the finished conductor then passes through extruders that coat it in layers of insulation and protective sheathing. For overhead conductors, the bare stranded cable is wound directly onto giant drums, some of them tall enough that a person could not see over the top. And then, the testing begins. This is the part that answers the skeptics. Samples get pulled apart in tensile testing machines to measure exactly how much force they withstand before failing. They get subjected to thousands of bending cycles to simulate decades of wind movement. They get run at high current for extended periods to see whether the conductivity degrades or the metal softens. They get bolted into terminals and then heat cycled hundreds of times, while engineers monitor the electrical resistance of that connection, watching for the creep problem that destroyed aluminum's reputation in the 1970s. They get sprayed with salt fog for weeks to simulate coastal corrosion. They get frozen and baked. The connection testing deserves special attention, because that is where aluminum historically failed. Alongside the new alloys, manufacturers developed connectors specifically designed for them. These use compression fittings rather than simple screw terminals, and they often include an oxide-inhibiting compound that breaks through the surface layer and keeps air out of the joint. In many designs, the connector is crimped with a hydraulic tool at a specified pressure, cold welding the connection in a way that a screwdriver never could. This is the honest answer to the electricians who say it should not work. They are not wrong about aluminum. They are describing a real material with a real history of real failures. What they are often not accounting for is that the failure modes were identified, isolated, and engineered around one by one, and that the installation methods changed alongside the material. It is not the same product wearing a new label. The alloy is different, the core is different, the connectors are different, and the installation procedure is different. That said, it would be dishonest to pretend the material is simply better than copper in every respect. It is not, and anyone claiming otherwise is selling something. Copper still wins where physical space is tight. Inside a crowded conduit, inside a control cabinet, inside the windings of a compact motor. There is simply no room to use a thicker conductor. Copper's advantage per unit of volume is real, and it is decisive in those applications. Copper is also still more forgiving to work with in the field. It bends more tightly. It tolerates sloppy technique better. And copper still has a better long-term track record simply because it has been in service longer. Some of the aluminum alloy conductor designs are relatively young in grid terms. A transmission line is expected to last 50 years or more. Accelerated laboratory testing is excellent, but it is not the same as 50 actual years in actual weather. So the honest framing is not that copper is dead. It is that copper's monopoly is broken. There is now a serious, credible, industrially produced alternative for a large category of applications where copper used to be the only answer. And those applications are enormous. Overhead transmission is the biggest one. Long-distance, high-voltage lines, the backbone of any national grid, are exactly where lightness and sag resistance matter most, and where the space constraint does not apply at all. China has strung these conductors across thousands of kilometers, including on ultra-high voltage lines that carry power from remote generation sites to coastal megacities over distances that would be international in Europe. Building power feeders are another major category. The heavy cables that run from a building's main service entrance up through the risers to distribution panels on each floor are large, long, and heavy. Aluminum alloy versions with proper connectors are lighter to pull, easier to handle, and cheaper. Notably, this is not the same as the branch circuit wiring in the walls that caused the historical problems. Feeders are installed by specialists with the right tools and terminated at a small number of carefully made connections. Now step back and look at the strategic picture, because that is really what this is about. Every kilometer of aluminum alloy conductor installed is copper that does not need to be imported. Multiply that by a national grid expansion program running for decades, and the numbers become geopolitically significant. A country that was structurally dependent on foreign copper for its electrical infrastructure has substantially reduced that dependency, using a material it can produce domestically in quantity. There is an energy dimension too. Aluminum smelting consumes a huge amount of electricity, which is often held up as a criticism. But that criticism actually reveals the strategic logic rather than undermining it. Electricity is something a country can generate at home. Copper ore is something you either have in the ground or you do not. Trading an imported resource for a domestically produced one, even at an energy cost, is exactly the kind of substitution a long-term industrial planner wants to make. And there is a grid dimension that may end up being the most important of all. The The world's biggest obstacle to renewable energy is not generating the power, it is moving it. Wind and solar tend to be abundant in places far from where people live. Building new transmission corridors is slow, expensive, and politically contentious almost everywhere. A conductor that doubles the capacity of an existing line without new towers or new land is not a minor upgrade. It is a way around one of the hardest bottlenecks in the entire energy transition. That is why utilities in North America, Europe, and India have been running trials with high-temperature, low-sag composite conductors of their own. This is not a uniquely Chinese technology and concept. Composite core conductors were developed in several countries. What China did was industrialize it at scale, drive the cost down, and deploy it across a national grid faster and more aggressively than anyone else. So where does that leave copper? Copper is not going anywhere. It will remain in motors, in electronics, in fine wiring, in anywhere space is precious, and performance per cubic centimeter matters. Global copper demand is still forecast to grow, because the total amount of electrification happening is so large that even with substitution, the absolute numbers keep climbing. What has changed is that copper is no longer the automatic answer. For the first time in a very long time, an engineer designing a large electrical installation has a genuine choice to make, with real trade-offs on both sides. That is a meaningful shift in an industry that has treated one material as sacred for over a century. The electricians who say this should not work are drawing on hard-won experience with a material that genuinely did fail. Their skepticism is reasonable and it should not be dismissed. But the material in these cables is not the aluminum that burned down houses in the 1970s, any more than a modern aircraft is the same thing as a wood and canvas biplane. Same family, entirely different engineering. The deeper lesson here is about how constraints drive innovation. Nobody in China set out to revolutionize electrical conductors for the fun of it. They ran into a wall. The wall was that a country of that size could not build the electrical future it wanted using a metal it had to buy from the other side of the planet at prices it did not control. So instead of accepting the constraint, they attacked the assumption underneath it, which was that copper was the only serious option. It took metallurgists working on alloy recipes measured in fractions of a percent. It took composite engineers borrowing techniques from aerospace. It took connector designers rethinking how two pieces of metal should meet. It took testing laboratories running samples through simulated decades of abuse. And it took manufacturers willing to build entire production lines for a product the market was not yet asking for. None of it was one brilliant invention. It was hundreds of small solutions to hundreds of small problems, stacked on top of each other until the impossible thing became routine. And that is usually how it works. The dramatic breakthroughs that seem to appear from nowhere are almost always the visible tip of 15 years of unglamorous laboratory work that nobody outside the field noticed at the time. Right now, somewhere in a valley in central China, a line technician is climbing a tower to attach a conductor that is mostly aluminum, wrapped around a core of carbon fiber, carrying electricity generated by a wind farm several hundred kilometers away toward a city that will use it to charge millions of electric vehicles. Every part of that sentence would have sounded like science fiction to an electrician in 1975. Today, it is a Tuesday. The metal that built the electrical age is not being thrown away. It is being joined. And for a lot of the wires that will carry the next century of power, the orange metal we all grew up assuming was irreplaceable is quietly being replaced. If you enjoyed learning how this technology actually works, leave a like and subscribe. Every week, we break down the engineering, materials, and industrial projects that are reshaping the world while almost nobody is paying attention. Turn on notifications so you never miss the next one. And there are related videos on screen right now if you want to keep going. So, here is a question for you. If you were rebuilding a national power grid from scratch today, would you trust a cable that your entire trade was trained to distrust? Let me know in the comments.